Okay, let's continue. So in the last class, we looked at sampling, issues with sampling like aliasing related stuff. So today we'll continue with quantization. And the general flow we'll take in this course is this. First, we'll try to understand ADC at a block level. Before that, we'll try to get a basic feel for the math behind the two operations that we do, that is sampling, quantization. Once that is done, we'll look at this at a block level, and we'll see how we can evaluate its performance, characterize an ADC and so on, those kind of things. And then we look at circuit level implementation. Okay. And of course, in the last class, we looked at the basic math behind the first operation we do, which is sampling. Today we'll continue with the second operation, which is quantization. And as we discussed in the last class, quantization is essentially discretizing the amplitude axis. So let us say your incoming signal can take an amplitude anywhere within this range, say some minus V reference voltage to a plus V reference voltage. Now, instead of you having to store any possible amplitude that the signal can take here, the idea is you divide this into finite number of segments like this, and you say any amplitude within this range will be assigned one particular amplitude level. Any amplitude in this range will assign another amplitude, and so on. And once you do that, you have finite number of amplitudes that you have to store, and this, as you know, can be encoded using binary bits. That is the basic math behind this operation. We'll see how we'll implement it later. And anyways, if we have 8 levels, how many bits do you think we need to represent this? 3 bits, I'm sure everyone knows. So similarly, if you have n bits, you can basically have n bits means 2 power n levels, right? So hopefully that is clear. So let's look at this input-output characteristic in bit more detail. So let me first draw the this guy. So again, the input, we'll assume that it spans this range minus Vref to plus Vref, and this typically is called the full-scale range, or sometimes called FSR. So let us say this is that from here minus Vref to plus Vref. Let's say this is 0, and let us say I want to quantize this amplitude axis into 4 levels. So essentially I will segment it like this. So what is this spacing? I mean, what is this value? No, I mean, don't go to jargons. What is the value? It's just a simple question, right? Minus Vref to plus Vref. There are 4 segments.
Minus Vref plus Vref by 4.
No, I am asking about the spacing between these two. I mean, a range is minus Vref to plus Vref. What is the total span? 2 Vref divided into 4 levels. What is the step? Okay. So this is 2 Vref by 4. And typically this is called the step size or delta, and in this case delta, as you saw, is 2 Vref by the number of levels, right? And in general, if I have n bit quantizer, which means I have 2 power n levels, what will this be? Instead of 4 levels, if I have 2 power n levels, what will that step size be? 2 Vref by
2n.
Fine. So let's see how the characteristic of this operation is going to look like. So let me see if I can. So let's say this is the input. Typically, input is denoted with Y. Output is V. And the simple mnemonic to remember is quantizer is essentially rounding off. So you take the input, round off, you chop off the tail, and you get V. It's a typical thing. So what I'll do is I'll basically normalize this axis with respect to step size so that it's easy for me. So this is basically 1 delta, 2 delta, minus 1, minus 2. Fine. That's all. So now any amplitude in this range, I want to round it off to some amplitude. What do you think is a reasonable value to round off anything in this range? 0 and 0.1, anything within that, what can I round it off to? 0.5. I mean, in principle, any value in this range is okay, but 0.5 seems to be a logical thing to do. Say, I will say anything within 0 delta and 1 delta, I'll round it off to 0.5 delta, and I'll normalize this also with respect to delta, so I don't have to worry about deltas everywhere. So this is half. And similarly, anything between 1 and 2, I'll round it off to 1.5, that's basically 3 by 2, something like this. Similarly, identical stuff happens in the negative side, right? So this is minus half. Okay. Cool. So in this particular example, I have chosen a case wherein 0 kind of is not an allowed level, that is at 0 you have this transition. You can also have a quantizer characteristic like this, wherein, let me just draw it and show, where 0 is an allowed quantized level, and then you can have, let us say, some levels here, some levels here. This is also equally possible quantizer characteristic you can have. So again, this is y by delta. If you have something like the one in the left, that kind of quantizer is called mid-rise quantizer. Again, for obvious reason, at the middle you have this rise, and this guy is called mid-tread quantizer. There are just some minor differences between the two. Again, one simple observation you can make is, if you want to have a symmetric characteristic, that is both on positive and the negative side, if you want it to be symmetric, you can have even number of levels here, right? Whereas here, since 0 is an allowed quantized level, you need to have odd number of levels so that you have a symmetric curve. That is one. And secondly, if let us say, if your input versus time is very small, that is close, it's very close to 0 like this, right? Basically, input is spanning this range, that's it. If it's a mid-tread quantizer, what will be the output? I mean, input is lying in this range, so the output is always 0. Whereas if I have input spanning this range, what will happen here? It will basically toggle between these two values, right? So if you want the output to be quiet when the input is not changing a lot, maybe you can use this.
How do we know that like at 0 the quantization level will be defined or not?
No, I mean, there is a discontinuity here, right? If you have your quantizer such that it, I mean, think of it like this, don't worry about how it's implemented. Mathematically, any amplitude in this range, you map it to 0.5. Any amplitude in this range, you map it to minus 0.5. So at 0, it is not defined technically, right? Okay. So yeah, so let's now, I'll take this mid-rise as an example and mid-rise, mid-tread. It's treading, like it's going, that's it. It's not changing. So let me. I mean, there is nothing like that. Typically, see, like these are the two things. Depending on what you feel is better for one particular case, you can use here. Right? Most common will be to use, generally you will use this mid-rise because even number of levels, so number of bits is also easier, right? Here you will have, let us say, 5 levels. To encode 5 levels, how many bits we need? Huh? No, 4 levels I need 2 bits. If I have one extra level, how many bit I need? I need 3 bit. You're kind of wasting a bit. So if you think like that, yeah, I don't use this. Again, there is nothing like, this is the thing for this application and so on.
So one fundamental question, like the V over delta is unitless, right?
Correct, yeah.
Yeah. And Y over delta is the input V minus
Correct.
V to V.
Yeah, both are unitless here. So let me take this. Cool. So let's try to see if we can analyze it further. So first of all, do you think this operation is a linear operation or a non-linear operation? Why not linear? I mean, how do you say if it's linear or non-linear? What is straight line? Huh?
For 0 to 1, it should be monotonically increasing.
No, here it's also monotonically increasing, right? Monotonically increasing is if I keep increasing it, is it changing? It is also increasing. Of course, in this range it is not changing, but it's not falling, right? It is monotonically increasing. Right? Huh? Yeah, superposition. So, I mean, simple cases, see, if I take some input here, the output is 0.5. I scale the input by some factor. If it's a linear operation, what should happen to the output? Output should also scale by the same factor, but do you see that happening here? If I scale the input from here to here, the output doesn't change. So it is non-linear. So for analyzing linear system itself is great deal for us. So if it's non-linear, you don't even have to ask. And of course, if you want to sit and do, you can know with pages and pages of math, you can rigorously analyze it. But that's not the point of this course. We just want to understand this and make circuits that do this. So what we'll do is we'll try to get a very simplified model for this operation. Okay. So let's say this is the input y. Okay. After quantization, I get some output v. I know my output is not same as the input. What is the simplest linear way in which I can model this? I mean, it just look like a block diagram, right? At a block level, what can I do to simply model this operation? They're very, I mean, my output is not same as the input. So what can I do here so that I can model this? I mean, if I have to model this operation mathematically using...
Add an offset and a scaling factor.
So yeah, so what you say, you can just add something here. See, quantization is rounding off. You add something here, that is the appropriate error that you are incurring in the quantization process to get the output. Okay. I mean, that's what I meant by model. Okay. So here Q is what we call as quantization error. Again, it's a matter of fact naming. Okay. So yeah, so if I give you a quantizer, how can I find this quantization error? I mean, I give a quantizer means I can apply an input, I can see what the output is. From these two, how can I find the quantization error? I take v minus y. So it's basically quantized value of y minus y itself. So we have decided that this is how we are going to model this. So at least let's try to understand more about this quantization error. So what I'll do, I'll try to plot quantization error also in the same thing. Like this. Again, it's y by delta. So remember, to get quantization error, I have to subtract the quantized output, or quantized input with the input itself. So I'll draw a straight line y equal to x. It's not looking straight, but something like this. So this is basically v equal to y, or v by delta is y by delta. This is basically quantized value of the input. So to get the quantization error, I have to take the difference between this step green curve and the yellow curve. So at 0, what happens? Let us say this is also q by delta. Okay. So at 0, what is the difference? Why is it 0? At 0, the yellow line is 0. The green one has a discontinuity. So even the difference will show discontinuity, right? And what will be the levels of the discontinuities? Half and minus half. Fine. So if I keep increasing the input, the quantized value is constant, but the yellow curve is increasing. If I take the difference, what happens? It falls. At this point, what happens? At that point, both the curves are intersecting, so it has to drop to 0. And once again, at this point, it will show a jump. So the same thing will keep repeating. Okay, I'll just quickly draw it. Something like this. Okay. Fine. Of course, if I keep increasing the input beyond the full scale range, let's say keep increasing the input like this guy is constant, but the input is increasing, so essentially this will also keep going beyond. Okay. cool. So from this, can you make any observation about the quantization error? Yeah, I mean, at least you see if the input to the quantizer is within the full scale range, what is the range of values the quantization error takes? No, it's not plus minus step size, plus minus delta by 2. Fine. I mean, this is normalized with respect to delta. It is plus delta by 2 and minus delta by 2. Right. So this is one observation I can easily make. This will lie in this range of minus delta by 2 and plus delta by 2. If my input is within the full scale range. Fine. Cool. But of course, this alone is not a great piece of information for us to do any kind of analysis or understanding. So what we do in practice is the following. We make some assumptions about the quantization noise, and I'll caution that these assumptions might not make any sense. It will sound atrocious, but it turns out in practice under appropriate conditions these hold quite good. Okay, that's all. So the first assumption is this. So firstly, you tell me if the quantization error here is a function of the input or it's an independent signal. Does it depend on the input? It strongly depends on the input. In fact, that is one of the things that makes this analysis easy. This is not some independent signal. Now, of course, you are in the process of making assumptions. Assumptions should make your life simpler. So what can you assume to be? If you give you a free pass, I want you to make any assumption on the quantization noise. What can you assume it? We'll assume that it's an independent signal. Okay. So we'll assume that Q is independent of the input. Okay. So which means I can treat it like a random signal. Again, there might not look any basis for this, but as we'll see, this kind of hold reasonably good. So since we treat it like a random signal, we also call this as quantization noise. So that's the first assumption we make. So now that we have declared this guy to be a random signal, how do you analyze random signals? What? Use some kind of statistical measures. So we need to say something about its probability density function. So again, you are in the process of making assumptions. What is the simplest PDF you can assume? I mean, Gaussian distribution equation is e power minus x square blah blah blah. What is the simpler distribution? Uniform, right? So we'll assume that this has a uniform PDF. So basically its distribution, or I'll say probability density function, is this of constant. And mind you, what is the values, the range of values for the quantization noise? Yeah, as we saw it's within this range. So this distribution looks like this. This is, let's say, PQ of Q and Q. And of course, we can now say what is this value? 1 by delta. Yeah, the area of this is 1, so this is basically 1 by delta. So now let's see if this assumption is indeed reasonable or not. For that, I did a exercise. So I basically generated a signal like this, a ramp signal going from minus Vref to plus Vref. I sampled it, I quantized it, and then I saw what is the quantization error I get. Okay. So this is the histogram. You guys know what a histogram is, right? It's a proxy for the probability density function, right? So here, if I normalize it by the number of sample size, I get the density. Okay? And as you see, it's almost flat. This is with a 6-bit quantizer, right? And if I do this with a 10-bit quantizer, it once again looks pretty good. But with this, let's not make any conclusions, because in practice we are not dealing with ramp signals. So let's look at sinusoids, because as you know, any signal can be thought of as sum of sinusoids. So I did a second experiment wherein I took a sinusoidal signal with a frequency of 201 Hertz. Okay. I sampled at 1000 Hertz. I did the same thing, I quantized it, took 1000 samples of this fellow and did the same experiment found the quantization noise and plotted the histogram, and this is what it looks like. Again, this is not exactly uniform, but okay. Again, this is with the 6-bit. Now if I go with the 10-bit quantizer, it's reasonably fine. At least if you zoom in from a long distance, it will look like it's flat. So this will make it tempting to again justify this assumption, but hold on to that because I did another experiment. Not necessarily. We'll see that. I'll make some statements, after that you'll understand. So I'll do another experiment now, wherein instead of doing this, I just change the frequency to 200 Hz. Looks like a harmless change. I do the same thing, nothing else changed. And if I do that, voila, the distribution looks like this. Just showing 2 fingers. And then again, this is the 6-bit. The 10-bit, at least I hope that it might be better, like he thought. It's not looking. So what do you think is happening? So let me put the 2 setups. This is the first experiment. Okay. The second experiment is where I just slightly change the frequency by 1 Hz. So what's the difference, do you think? So
same quantization levels were repeated because the frequencies are multiple of
Okay, here they are saying that looks like at least the simple mathematical observation is this guy is a multiple of this, or I would say this guy is a divisor of this guy. So let's see what happens. So let's say if I do this sampling, if I sample the signal at 1000 Hz, what is the discrete time sequence I get? Sine of 2 pi times 201. T is replaced by NTS, N by Fs. Fine, this is the discrete time sequence which is getting quantized. So here, what is the periodicity of this sequence? Or with how many samples do you think this signal is periodic? 1000? After 1000, this argument repeats as a multiple of 2 pi. Hopefully that is easy to see. So the periodicity here is 1000 samples. Right? So let's do the same thing here. If I do that here, what do I get as a discrete time sequence? Sine of 2 pi 200 into n by 1000. This is basically n by 5. Yeah, what is the periodicity of this fellow? It's periodic with just 5 samples. Right? So in the first case, when I actually took the signal, quantized it, and took 1000 samples of the quantized data, all the 1000 samples that were fed to the quantizer were unique, because the signal repeats only after 1000 samples. If I take any set of 1000 samples continuously, it's going to be all unique, right? Whereas here, although I take 1000 samples and quantize it, how many of them are distinct? Only 5 are distinct, right? So essentially, if this was the quantizer characteristic, in the first case I was exercising all possible levels of the quantizer. In the second case, I had only 5 unique amplitudes that were getting quantized. So I was probably exciting 2 or 3 of these levels. Okay. So that's the difference. So the bottom line is that as long as we have what are called BC signals, again this is our loose definitions. By BC signals, I just mean that the signal spans the entire range, excites all possible quantizer levels, and there is sufficient variation from sample to sample. It is not repeating, the small periodicity. As long as we have these kind of things, looks like the quantization error PDF is almost uniform. Okay. It's called BC signals technically. I'm not going into a lot of rigor here. You just assume that it is a case where signal spans the entire range, exciting all quantizer levels, and there is sufficient variation from sample to sample. So now at least we know for these cases, the PDF is uniform. So let's just convince ourselves of that fact and try to understand more from that. So let me sketch the PDF once again. So this is the PDF, right? So now that we are convinced that this is the distribution, let's make some observations. What is the mean here? This is a probability PDF. What is the mean? 0, right? Because it takes both positive and negative values with equal probability. What is the mean squared value? How will you find? And remember, mean square value is basically the power in the signal. Okay. Why is it 1? How do you find the, I mean, it's expected value of, how do you find it? If I give you the, so remember, it's basically q square times PDF. I integrate over all possible values of, I integrate with respect to dt, right? And if I'll let you work out because this is constant, it's a simple integral, you find this will be delta square by 2. So this is what we typically say, the quantization noise power is delta square by 12, where delta is the step size, as you know. If it's n-bit quantizer with a range minus Vref to plus Vref, delta is this. Okay. So as of now, we have gotten at least some information on the quantization error, quantization noise.
Power is defined as expectation of q square or like x variance of q?
No, there is a difference. Variance of q is basically expected value of, wherein you remove the DC offset and do it. But power includes DC, right? If a signal has a DC component, there is power to it. If it's a zero mean signal, then variance is same as power. Okay. Otherwise, power is basically mean squared value, which is mean of the squared value, right? Expected value is mean. It's mean of the squared quantity. That is basically the power. Okay. Cool. So now we have gotten some information on quantization noise. So now we can try to see how we can basically characterize an ADC, right? And this seems to be like a reasonable thing to do. A good ADC, as you know, should be having the capacity to resolve with more and more bits, which means I should have more and more n. So which means this term should be smaller or larger? Should be smaller. It's a quantization error power. If lower that is, you can say better is my quantizer or better is my ADC. But this alone will not paint the full picture, because in practice we are not only interested in the noise power, we are also interested how large my signal power can be, right? So here again the range is minus Vref to plus Vref. So I can have a sinusoid like this. That is a maximum sinusoid I can feed into my quantizer. So what is the maximum power of the signal for a sinusoidal? I mean, this is the signal. It goes from minus Vref to plus Vref, a sinusoid. What is the power of the sinusoid? Amplitude is Vref. So hopefully this is clear. So as you know, we are interested in the signal to noise ratio. So here we have something called signal to quantization noise ratio, or I would say SQNR. And here this is the maximum signal power, mind you, right? So I will say this is peak signal to quantization noise ratio. Okay. So I can find this. My signal power is essentially Vref square by 2. Noise power is delta square by 12. I mean, it's a simple algebra. I'll not do this. You work out, you get something. Okay. And you typically signal to noise ratios are expressed in dB, because you have to express a wide range of values, so it's better done in log scale. So if you do it in dB, this will be 6n plus 1.760, where n here is the number of bits you have for the quantizer. Again, I have to clarify, this is peak SQNR for sinusoidal signals. It is just for sinusoidal signals that we have made this calculation. Oh, I mean, this is fine. From here, you know delta, you put it, bref goes off, and then you have just, n and constants, and then you take log. I don't want to spend time on doing basic math here. So now you tell me, if I have a 10-bit quantizer or a 10-bit ADC, what is the maximum sinusoidal signal to quantization noise ratio I can get?
61.76.
Yeah, about 60 to 62 dB, right? So now let me rewrite this. So I know that SQNR is 6n plus 1.76 dB. From this you can calculate what is your resolution. So you can say this is SQNR. So this is typically called the effective resolution, or ENOB, which is the effective number of bits. Okay. Again, this is an important metric for ADCs, because see, let's say for all that matters, I can design a 2-bit ADC, okay, and then randomly have 8 other bits, connect randomly to ones and zeros, put it in a black box, and tell you that, hey, this is a 10-bit ADC, go and use. Just because you have 10 digital bits coming out of your quantizer, it doesn't mean that it has a capacity to resolve my signal with 10 bits of resolution, right? So that's why this is required. Of course, what I told is a exaggerated, degenerate case. In practice, let's say you try to design a 10-bit ADC. Ideally, the peak sinusoidal signal to quantization noise ratio is about 62 dB or so. But due to a lot of circuit non-idealities, you might find you might not be able to hit this. It might be slightly smaller. So in that case, you quantify the effective resolution using this ENOB. Okay. And as you see, for finding the ENOB, we rely on sinusoidal SQNR. So if I were to measure my SQNR, what should I feed to my ADC? I should feed in a sinusoidal signal at maximum amplitude, and then at the output, again I'll have some quantized sinusoid like this. I mean, it will be discrete time, I'm drawing it smooth because I'm lazy. So this will get something like this. And from this you are supposed to find what is this ratio, which means you are supposed to distinguish signal from the noise, right? And from the time domain, can you distinguish what is signal, what is noise? Exactly. I mean, okay, you can say, oh, this looks like a sinusoid, but do you think it's exactly possible for you to say my signal has this power, this noise has this power from time domain?
So with respect to time, won't the noise be random so we can identify?
No, that's okay, but if I give a sinusoid, it is going to quantize like this, right? This is what I'll get. Of course, if you subtract this and this exactly, you will find some random quantization noise. But the point is, you cannot exactly measure what is the noise from this alone, what is signal from this alone. Is that clear? So in time domain, you are not able to do. So what do you do? Go to frequency domain. So I always say, if your mom doesn't give pocket money, you go and ask your dad, something like that. So you have to do it in frequency domain, and that's why it is important that you should be comfortable with basic frequency spectrum plotting, spectral analysis and stuff.
One fundamental question from the linear definition of the quantization
Okay.
error.
Mm-hmm.
So, like, we first defined quantization error, then we proceeded towards quantization noise.
Mm-hmm.
So, like, what were we actually doing? Like, we were like eliminating the concept of quantization error as a whole. Like,
No, quantization error is there. That is treated as a random signal or a random noise.
So, but the definition, by definition, we are saying that it's a subtraction of the.
Correct. It is subtraction of that. But that's what I'm saying, right? Ideally, it is subtraction of that. That subtracted quantity we are treating as a random signal now. It might not make any logical sense, but that is the easier way to analyze. And this holds quite good, as we saw. Okay.